Okay, we're good there. And so what we got over here? We're all streaming. Okay. Well, hello, everyone. Um, we are currently streaming. I guess we'll go and we'll talk about. We got a few minutes before we start. But feel free. The few people we have online right now. If you want to say hi, let me know that chat's working, audio's working, and you can see the screen okay. Otherwise, we'll talk about PCIe soon. Looks like this is more going to be a smaller session than usual. But hopefully we can have some good discussions about PCIe, how to access it from the processor side, how to access it from the FPGA side, and come in the utilities that are provided by the FPGA vendors, and how you can, I guess, bypass those utilities to do your own PCIe stuff. Back. Okay, that's everything fine. We'll give it another 2 minutes, and then we'll go look at um, we'll go look at this example design, get it running on the Raspberry Pi, and then play around with a few different things. Go to my dashboards. They're doing good overall. Hi, hello, Alamar from YouTube. I'm glad you could join us. Have you used PCIe before on an FPGA? I guess a custom PCIe solution. I mean, it's usually an FPGA. You don't really have opportunities to do custom PCIe stuff otherwise. I mean, I guess you can play around with PCIe drivers, but it's not an easy skill to find hardware to play with. Okay. Okay. So, welcome to the stream. This is kind of more of me exploring different example designs provided for different FPGAs I have around. Today I wanted to focus on PCI. I really like PCI. I think it's a really fun interface. It's one of the if you're doing a kind of a processor, FPGA, GPU type of system, accelerator, PCIe is basically required. And it's a really it's not well understood. It seems like kind of a rare skill set. And I mostly just want to learn more about PCIe and how I can understand it at a lower level. I think my goals is to build a kind of a soft processor in these FPGA, or program a soft processor to do a kind of like a software defined PCIe point, our root complex, our bridge, and stuff like that. I'm really curious to what happens if we put a programmable soft processor and do some PCIe packet processing. I wonder if we could maybe use something like the P4 processing language. It's great that Alamar from YouTube, you got a PCIe. You're doing PCIe in a Vertex board right now. That's great. You're using example design. I find the driver, at least the XDMA driver, tricky to modify. By the way I word it. How do we go in and build our own? I do want to learn how to do more custom PCIe solutions from scratch. I do think that the XDMA core, while convenient, it's probably overkill for a lot of what people need. You still can get really good bandwidth, but you don't need so much of the control overhead or the DMA engines to be able to get a better flow. Okay, so I'm FPGA Zealots. You can find me YouTube, X, Twitch. You can also find me as Andrew Wilson on LinkedIn. Some disclaimers before we start. I am not employed by Altera. This is not a paid stream. This is loaner hardware from Altera, and I'm just taking some time today to explore some example designs that I'm interested in. I do not offer official support for these products. This content in this channel is created for information purposes only, and all opinions expressed on this channel are my own. So today we're going to be looking at the Agilex 5 FPGA PCIe example. This is, somewhat similar to kind of your basic PCIe example that you would see on most FPGAs. It's just going to do a direct memory map of the first bar space to either an AXI or Avalon or Wishbone address space. And you can read and write to that address space as if it was directly memory mapped. And that's what we're going to do today. We're going to use the Agilex 5, they call it programmable I/O PCIe example, get it working on the Agilex 5 modular dev kit, and then connect it to a Raspberry Pi CM4 that's on my little compute blade on the left of that image. And we'll dig down to more of this stuff and walk through it. So for the PIO example, like I said, you're going to have a basic PCIe link. We go to this hardened block here, this PCI Express block, and it's going to take the TLP. Well, it has a configuration there. So the default configurations, this hard block, this PCI hard block communicates back to the root complex, tells it's the configuration, the vendor ID, the product ID, the bar spaces, all that good information. It negotiates that configuration with the root complex. And then I would say, the data transfers, those TLP packets, the transport layer packets, are sent over this AXI stream interface in the middle. Use the mouse. Over this AXI stream interface in the middle. And then it's converted to a Avalon master, and then that Avalon master is just connected to some local memory. So this is how you can do like a read and a write off of the bar 0. And we'll show that configuration on the IP core. What's the best? Before we go into digging into the packets, let's go ahead and open up the IP core. And I just want to talk through. So we have a zoom in on the right, so you can see what's happening as I go through here. So we're just going to go through the configurations real quick and how you can set up the core on the Agilex 5. And this configuration is actually very similar to what you would see in Lovato for the Xilinx IP core, and even similar to what you would see in the Polar Fire. The Polar Fire, those settings are a little bit more, I don't think they're complex. The Polar Fire is usually not as complex as a configuration, but basically the same things. We're going to choose our speed and our width. We can do endpoint or root complex. And there is the TLP bypass mode, which I do want to try someday. And instead of this hard block doing the negotiation of root complex, all TLP packets will be sent to the fabric, and the fabric has to negotiate the configuration. I think this would be useful if you want to dynamically change your information depending upon some other settings or something like that. This can also be useful, I think, if you want to do like a TLP like bypass to another endpoint or potentially a bridge or something like that. It'd be fun to explore that. And then for the other PCIe configurations, there's a lot of things that you can go. So it's definitely good to look at the user guide as you go through all these different settings. But most of the data, the TLP packets, the pre-processed TLP packets are going to go for this AXI stream interface. It's also an AXI Lite interface. I do not know what it does off the top of my head, but we're mostly focusing on the AXI stream interface with all the default settings. And then here are kind of more of the more generic PCI settings that you would see in a lot of different areas. So we have each bar space, and you can do 64-bit. If you do 64-bit, it takes up bar 0 and bar 1. But you can do 32-bit. We're going to do 64-bit prefetchable. We're going to do 64K bytes, so 16 bits of addressing. And then that's basically the same across all of these. Now what the expanded ROM size does. Interesting. I think you can include like a ROM inside the core. Here's the critical. These are very useful for driver software. So when you have driver software in your hosts, your root complex, you can use the vendor ID and the device ID to determine which driver software it's going to use for which component. We're going to be interacting with the PCIe through Python today, and we're not using like an official driver, so we're not going to really rely on the vendor ID or device ID, but they do need to be non-zero for Linux to let you access them. If these are all 0, Linux has a feature in it where it won't let you access the memory space. So you want to make sure these are at least non-zero. And then the capabilities, there's a lot of tabs in here, but payload size, then we have various different other configurations for the interrupts. There's a lot of, I'd like to look more into like all these little configurations, but there's a lot you can explore within the system. Hints, processing hints. That's interesting. Physical function. Okay. And then we have configuration. So we've already built the example design, but so if you just do default settings and then you go to development kit and you select the modular board, you generate the example design here. That's how you can get the example we're running. So I'm going to minimize this. Let's pull up the example design here. Take that down there. Probably take that down here. Like kind of like we showed in the other picture on the right here. This is from the example design user guide. We have the hard processor and then the PIO core. The PIO core is not really exposed in here. You can when you double click this and you look at the features, it doesn't really give you much. There's not much settings you can change. Let me see if we can open up the, where did I put it? This one right here. I want to view properties. There it is. Okay, so yeah, the PIO, you have a data width, and you have a device family. That's all you really get with a PIO. Add that back over there. That's really what you get there. And so our data, our TLB data, is being sent over these two lines. So we have our RX stream, which is bringing over our TLP packets. Then over here we have the TX, which is doing our transmitting back kind of any, I guess, completion packets to the root complex. So overall, I mean, there's a lot of lines here, but those are mostly the two signals. Let's exclude that, and that. We have other streams. We have the control stream here. I wonder where these, like, they're both inputs. What are they going to do? That must be something else. But that's mostly what we're going to be focusing on. Okay. Okay. So that's the other design. We don't have to worry about that for a second. Okay. Any questions about that? So we have the example design. We built it. We programmed the system. We can go jump into the Raspberry Pi real quick. Right here. So when you program the FPGA, make sure you do like a soft reboot so it properly enumerates it. Let's go ahead and do LSPCI. We can see we have the Broadcom bridge and the Altera device, the LSPCI-T. We can see here's the bridge and here's the device. It's not very descriptive. Now if we do sudo lspcie dash s 0 0 0 fpvv, we get the information. So what's the critical information here? You get the vendor IDs. So where did that one come from? So if we go back to this guy right here, I want to see device identification. So the class code is 0FFF. So the class code is FF00, and then we have the Altera probably comes in other places. I don't see where the... But here's our first memory space, 64-bit prefetchable, 64K. Because it's 64-bit, it can be assigned a 64-bit address. If you notice, that is a 64-bit address. Can I highlight it? Not easily. And then we can go look at the other settings. We are downgraded to Gen 2. We are downgraded to 1 lane. This is a restriction of the Raspberry Pi and not of the FPGA device. We can go up to Gen 3 and the width of 4. Interesting. Payload size 128 bytes. Max read request is 512 bytes. I don't know how that works. That's about everything we need here. Okay, that's mostly all the information that we have listed for this device. And now we're going to do some simple reads and writes. I usually do this through, I have a Jupyter Lab page. So I have Jupyter Lab running here. I'm just going to show you what we got working for that. So in our Jupyter Lab page here, I'll retitle this. We're using this utility to interact with the system. Today, instead of devmem, I'm trying a more useful pointer that goes directly to the base address of bar 0, resource 0 for the PCIe device. So basically what we're going to do is in Python, I'm using privileged instructions. We can memory map the system. We're going to memory map the path to bar 0. We're going to open that memory map with read and write permissions, and then we're going to take that pointer and set up a numpy pointer towards it, and then basically we're going to just do a read and a write treating it like an array, and we can read and write to that array very easily. So that's how we're going to access the device a little bit. And we have a close. I think we have a close. Close. Hello from Twitch. I got Sub-Zero from Twitch. So what we're going to do is we're going to get a numpy going. We're going to import our PCI mem utility. And since it's base address, so if you're doing this is for if we're using /dev/mem to access it. But since we're doing, star, or we're doing sys bus PCIe device, name of device, something like right, and then we're gonna do resource here. We're gonna do an address offset of 0. And then we can read from the device. Let's go ahead and read an address. So I kind of already gone through, but we can read different addresses. So that's 0, and then we can write to that address here. And I mean, you can't really tell that we're reading and writing to PCIe. I'll show that in a second. But we're interacting with the device, and I'll show how the TLP packets break down. More hellos from Twitch. And we have a question from Twitch. Speaking of the Agilex 5, have you checked out the new D Nano 20 from TerraASIC? So I've talked to TerraASIC. We'll probably be looking at an Agilex 3 board from TerraASIC later this year or next year. But I've looked at the DE25. I think it's an interesting SoC platform. I really like PCIe, so I really like the modular kit, but I've looked at the DE25. What do you like about the DE25? I mean, I guess we can go slap that down, really. DE25 Nano. Well, this one didn't have an SoC, right? Let's see. No, it has a processing system here. So, Sub-Zero, what do you like about the DE25? The layout. Let's go back to specification, grab that link, bring that over here. So the DE25, I guess here's the board. You can look at the ports later, but description, you get LTPDR, SDRAM, 2 DDR sides. So it's probably I'll have to look at the price in a second. But you get 2 UARTs and JTAG. That's really good. I just really like PCI. Motor controller and other cards. So I'm looking at the layout real quick. SFC, FPGA, DDR, HDMI. Yeah, I've had fun with using like what do you do? The like a USB SDR over the system as well. That'd probably be a really interesting application here. A little software defined radio a process where you take the data and you ship it to the processor. Or maybe a side channel with their other ports. Okay, and do we have the price setup? Oh, it did say 250. I think for the resources you're getting, that's not bad for 250. I do. What was the? How many LUTs are we getting? 138. Yeah, that's pretty good for 250. That's pretty competitive with other stuff going about. Okay, yeah, there's our quick conversation. Sub-Zero, if you have any other comments about the D25, feel free to leave them. Okay, so you're looking into an Altera dev boards, and you probably want to look at an Agilex. There are the really small Agilex 5 and 3 boards that have the feather format. That also from TerraASIC. Let's see, all FPGA boards. That's going to be, I think it's going to be a trend. So let me go find the board real quick. So trends, Altera FPGA. It's still kind of an expensive thing. Yeah. So we were from Max. Where they had a really tiny Altera board or Agilex board. That's a song. No, it was Arrow. Yeah, Arrow Agilex 3. Well, there's some really small feather. Agilex feather dev. Where they're really tiny ones. I'll have to look for them again later. But yeah, I think for a price point, you get a good amount of peripherals on that. So I have an Agilex 5. I'll be looking at Agilex 3 later. If you want like an affordable one, the Deca, like clone J board. If you can find a used Deca on like eBay, the price was really good for it. Let me see. Does eBay have any? eBay Deca FPGA. I'm not seeing it on there. Okay. But yeah, those are older boards. The Deca has a like a Cyclone. Was it a Cyclone or a Max 10 FPGA? I think you might want to lean towards. If you're going to industry, you probably want to lean towards an Agilex 3 or Agilex 5. If you're going to hobby or academia, the Cyclone 10, the Max 10, the Cyclone 5 are all still really good FPGAs. Okay, the Deca has a Max 10 FPGA on it. Okay. Okay, write that real quick. Okay, so next we're going to talk about TLP packets. If you joined us in the last, I don't know, 20, 25 minutes, I'm FPGA Zealot. We're going over a PCIe example for the Agilex 5 FPGA using a Raspberry Pi. Look at the picture right here. So we did a quick example of showing how you build the project, getting it to read and write. But I want to talk about the TLP packets. So TLP packets are, industry standard for PCIe. PCIe uses these TLP packets to talk to each other, and the Altera PCIe core provides you the TLP packets plus additional information. So it gives you 32 bytes, which is going to be 8 words, 8 D words, we'll say, since that seems to be a common reference. And yeah, 8 D words. And the first 3 D words are going to be your first 4 D words are your traditional TLP packet header, which is a format, a type, some tag information, some attribute information, a length. And that's going to be in the bottom portion of your T data that's coming across. And then after these 32 bytes, then you have the data. So this byte 32 to 63, that's going to be the payload package. And we're going to look at this in more detail and then play around with a few different examples. So we have signal tap set up. Signal tap is like Xilinx's ILA core, whatnot. Zoom out a little bit. So let's go over here, talk about this stuff. So we added the TX, we have the RX signals right here. We have, you know, RX keep, RX last, RX valid in the data. Same with the TX valid, last, keep in the data. And these are split by D words at 32 bits. And then we're going to trigger off of the RX valid being high. So we're going to have that set up. So what we're going to do first is we're going to write a very basic message over over the little Raspberry Pi Python interface. So we're going to do a write first, because the write's the most basic message. And we're going to write address 123, and we're going to write 5, 6, 7, 8, 9, ABC, right? Right. Okay, so we're just going to write this. And if we go back here, we now, yeah, okay, the data's set up. So what we can see here is 4 right here. That's a write packet. The 1 is the length. Let me pull up the magnifying glass again. Right. We want to grab the bottom, I guess, up here. The tickle console, we don't need a hierarchical display or the data log. And what we're going to do here, sorry, I want to make this pretty so you guys can see it. So have that down there. And then we'll just put this window right here. Okay, so, okay, everyone can see what I'm talking about now, hopefully. Let me go check. Okay, so over here we have our different D words, and the very first D word down here is going to have the format and the length. That's a mask, I think. I'm gonna have to look that back up in a second. And then we have the address 1, 2, 3, 4. I believe these are just the upper bits of that are, we can't use those bits, so they just set those high. And then there's additional 5 data words right here that are all 0, and that's because where all the other important information, like the virtual bar, the physical bar, the other stuff is all 0. So the rest of our header is 0. The data comes down right here. We have the T last goes high right here, and we see that we want to take the 4 bottom bytes with that's going to be the T keep. And down here we have our data being 5, 6, 7, 8, 9, ABC. So that's the data we're sending across. And we look at going back here, that's our data. We're using 126-bit bus instead of 256, 128 instead of 256. That's why our data is 3 cycles instead of 2 cycles, like in this example. Okay, the type of request. Okay, if we want to look at the type of request, we can go here. Okay, write. Okay, the first BE. Just to explain what that data is here. Which of the 4 bytes in the first G are valid. Okay, yeah, that's a mask of what data bytes are valid. That's good. I don't know why. Okay. Now, I mean, we can do a different write real quick so people can see what the examples look like. So let's say FFC, and we want to do cafe taco. Now we head back here. We're transmitting to address FFC, and the value is cafe taco, and that's what we're writing to our BRAM. So next, let's do a read. So let's go ahead and read that address of 1234. We can look at the read request. So the read request right here is saying length of 1 and address 1234. We can go see what the 5 is. I have to go to that other web page real quick so we can see what that is. Going to our basic read request. That's going to be the tag. Okay. So the 5 is the tag that we have to return for the read. So we have the 5 there. Now we're going to zoom out real quick and find the completion. The completion is over here. So here's our completion packet. It's a 4A packet. And we're going to say length of 1. And that 5 right there is our tag that we're returning. And then we have the bottom byte of the address, which is 34. And then our data, which is right here. Interesting that the T-keep is high for these things. 1, 2. I guess those are the next addresses. I'm not sure why they're included in here. Then 380. Oh, that's, yeah, it's reading all 4 addresses, but the T-keep is there. That's interesting. So if we read an address back, we should I want to see what happens if we read an address back. But that's the return request. I should probably show you more about the return request, which is over here. So the return request is listed here. We have the 2A, the length, and we have the address, and we're returning the tag. But if we go back here, and if we go back an address, I'm really curious of what it's going to look like. Yeah, so it looks like it does a read. So it's reading all 4 words. So it's doing a burst transaction when you do this. So we probably can do larger reads and larger writes. I gotta remember how to do that with the Python. It's a little bit more complicated than the array we set up. But we might be able to do bigger reads. I mean, we can try to do that real quick. Maybe we have time. We can go try to request a larger read. But there's our PCIe return packet. And we're not doing any fancy DMA for this example. We don't have like a DMA engine with descriptors, doing scatter, gather. We're doing direct memory reads and writes. So if you're doing like a basic PCIe system, you're trying to control and status over PCIe, this example works really well. If you want to do DMA, you're going to need something that generate those TLP packets to support larger transactions that the FPGA can handle. In this situation, the processor is driving this communication. So this kind of processor-driven PCIe. Most DMA for a lot of these systems are going to be endpoint-driven DMA, where you tell the FPGA, hey, I have data in this address, go ahead and read it, or I made a buffer for you, go ahead and write to this buffer. And the PCIe, or the FPGA, does the data, is the one that initializes the data transfer to the root complex's memory. And a scary thing about PCIe, if you don't have security, the FPGA and the processor are basically sharing memory space, depending upon how you define it in both systems. But both systems have access to each other's memory space. And that can be really useful, can also be really dangerous. Really quick way to mess up your system, especially if if you have some critical data or BIOS or directly memory linked and the FPGA writes to it, clobbers some critical information or register files, and your processor, it may need a like a reflash of the BIOS or something crazy. Okay, let's go try to do a read of 4. I'm really curious if we can do like a larger read. So what we're going to do is we're going to access this array. Can I access the array? Can you do that? Seems unhappy with that request. Okay, let's try again. So numpy access this, try to read, do perform a read. Can we do that? I hope we can do that. Sweet. So we can do that. Now, can we just request? Okay, let me see if we just do the request. Interesting. Now we go back here. Oh, it's still requesting it like one by one, maybe? Let me see if we back up. Do we see the other transactions? Yeah, we see the other transactions. Let me see if we can figure out some. Totally played around with this before. Python way to transfer multiple words in one line. It's also how the processor translates it. So in this situation, the processor is just doing like a byte at a time, right? So address 4 to here, but we're only sending, the mask is only 1 byte and the length is only 1 byte. How do we get the length to be bigger? Okay, let's try something crazy. Okay, let's see if this works. May not like us. So what happens here? Does it do a pointer? Yeah, it's not requesting more data. We could try to increase the size. How big are we? What size? Let's transfer this to just 100. Actually, no, that should work. What if we do bytes? It just did it. Okay, let's go back to a single transaction, see what happened. I want to write this. Okay, we're back to a single transaction. And I want to grab all the data. Now we have a bunch of transactions, but these are all still 1 byte. Okay, let's try to do bigger words. Okay, so what we're going to do here is we're going to increase the size by that much, and then try to do a transaction like that. So let's restart our kernel. I just want to get a 4. Just give me a 4. Import this. Import this. We'll set this up. I'm not going to do a read or write, because that'll break things. Did that wrong. It's no, UN 128 doesn't exist. Let's see. We can try double size at least. Besides trying to make a new type. Okay, let's go back here. We'll do, I just want to see a double word. Okay, or we can just re-import it. Okay, let's restart the kernel. So we can get at least 2 words in a transaction. I really want to see 2 words in a transaction. So we're gonna bring this in again. And if we do this. Okay, so that's a 64-bit value. Now we go back here. How did you handle that request? Did I request 2? It still says 1. Interesting. What the heck is on this? Okay, it's just doing it twice. Interesting. Well, it's only saw 1 request. I'm gonna have to find where I did a bunch of PCIe testing to try to play this out better. Okay, so for now we can only do 1 word. I'm gonna have to figure out how to do larger words. Let me see. Copy to a file. Okay, we're going to try some vibe coding to see how we can do this. So we're going to restart the kernel real quick. And I want to see this work. Okay. We do offset of 0. We do that size. And let's try this. So we're going to open the mmap thing, do an access read, copy to another file, and see what we get out. Okay. Refresh, copy bin. Give me a terminal here. Let's do xxd -e, right? -c 32 -g4 copy bin. Deadbeef. Oh, looks like we wrote deadbeef to the first 4 addresses. Okay, how did that look here? I want to see. Did we do bigger transactions, or is it every single? Okay, we have a bunch of transactions. That's great. They're close to each other. But we're still doing 1 word at a time. I wanted to do a multi-bit transaction. We're still just transmitting 1 word. And the dead beef is only 1 address. Is it sending it again over here? It's like it's requesting 4. It's only sending 1 back because the address jumped. See the address jump there? So yeah, the address jumped. So that PIO is not working like expected. These should be incrementing, but they're not. So it's just reading 1 word over 4 times. Is that an issue with the OS, or is that an issue with... Oh, that's weird. Anyone have suggestions for PCIe writing? This didn't work as I expect, or was different from what I expecting. Everything else seems to work pretty well. Let's try doing this and see if we... That's dead beef. Okay. And this one over here. Yeah, it's just moving up. Okay. So that's the processor doing the request. The processor does not like what I'm trying to do over Python. It's doing 1 byte request, but it should do 4 byte or 4 word request, but it's only doing 1 word request. Which is weird. Okay. Let's see if we can get another vibe code example. Any other questions about PCIe before we, I guess, close up? Mostly just playing around at this point. Here's an example, the signal tap. Anyone else have any suggestions or questions about PCIe? I guess the next thing is to actually write a useful driver. That's about the only thing we can do next. Okay. Okay, we'll probably stay on for another 10 minutes while I see if I can figure out a good Python example to try. Okay, let's try this. I like this method right here. So we're going to copy into buffer to offset 0. Okay. Let's try resetting the kernel. Okay, let's just not close it. You happy now? I'm not gonna close it. Mmap is not defined. Oh, let me get. I got these guys. Okay. Did we get anything different from that one? Okay, we're only sending one still. What do we got here? Yeah, we're only requesting one. It's just so weird. I want to try to request more, but it's the Raspberry Pi. It's not requesting more. And we can look at 0, and it's going to be... Oh, that's not what I was expecting. Oh, it's a byte array. 3. Sorry. Okay, I'm sorry. Dead beat. Okay. And if we do 15, what do we get? Yeah, it's coughing like that. It's just so weird. Issue with the Raspberry Pi OS. I guess we could try this one. And then close. Fine. And what do you do? Okay, yeah, whatever. Let's do that. So is it snapshot? Yeah. An array, 32-bit. Still copying everything, every word. Oh, we want to do 0. Like that. Yeah, it shouldn't be doing that. Ah, that's weird. Raspberry Pi issue, I guess. Okay, let's play around with the address again, make sure we haven't broken something. We'll try this address. See. Oh, yeah, the reads are working. I just want to make sure the signal tap. Yep, the signal tap is changing addresses. Is there a dev entry for PCI for block transfers? I mean, with this basic memory map, I don't think there is. And we can go look at what we have. I think it's just specified as a resource, right? So we have resource 0. Is it ls/device? Might be something to do with this max payload size. Maybe that's a configuration of the PIO. Okay, well, I can set it up with a different system that we can do more interesting transactions on it. But I think that's probably good for now. I'll look at trying to write, a better driver. How do we go about writing a driver that supports burst transactions? Wait a minute. Let's just see if there's some C code that's available. They gotta have driver software for this. On-chip memory, PIO application. Yeah, I don't see quick start guide right here. Simulating, design, compiling hardware program, installing the Linux kernel. Well, we got a Linux kernel. Where's this Linux kernel? Okay, navigate to under the software driver. Okay, we can go and try this out. Let me see where. So let me just open the folder. Yeah, wait for a second. So PCI Gen, example design, software, kernel. User, example, API. Okay, yeah, let's try to build this. They may not like us. Okay, so what we're gonna do is we're gonna transfer this out of the system and then to the Raspberry Pi. We can do that. So we gotta go here real quick. So we're gonna copy. Well, first let's make a directory. We're gonna make that in the mount. I don't know. Mount main OS. Do put answer. So let's cd into PCIe Intel PCIe example. We have the software folder here. We're going to copy -r software into mount main OS user. Okay, cool. Now we're going to close this. We're here, so we're gonna cd. Huh. Oh, what? Come back here. Okay, full screen you. Okay. Yeah, it should be there. Maybe we can't see it. Maybe it's hidden. Okay, so it's so it's sudo chown pv dash r. Sorry, this is gonna be a little annoying. Okay, can we go and yeah, we can go into that now. We have software. Okay, we can move this. So we're gonna sftp into pi at config 61. Cool. 192.168.0.61. Yes. Okay. ls make a directory. Altera. cd Altera. I didn't spell Altera wrong. So we're going to put where? Can we do like a dash R? Okay, cool. Now back over here, we can cd into cd into software. Okay, we have our software folder. Let's go to the kernel. Okay, back to these instructions. What are we doing here? Installing the kernel driver. Okay. So Linux. We're gonna copy this. Sudo. Um, oh. Yeah, this is why I don't like messing with kernel drivers. We have an issue with that I do not want to fix at the moment. Okay. I got this requires some kernel driver work, but if we got it working, oh, that's a okay. We want to try to fix this real quick. I guess we could fix it real quick. We can try to fix this. So this is going to be dma.c. So let's go to refresh array kernel Linux dma.c and okay. I want to do this. I want to fix this. So what line are we going to? Be line 181. So 181. We want to do get real. So we're unhappy with okay. What do we want? I don't really care for any of this. Okay, what's it saying here? Undeclared TS. What's this? I think if we just make these both like this, I think we should be fine. Ah, it built. Yes. Stupid kernel header values. Okay, cool. Back here. Did it get installed? Installed. Cool. Okay, we're good to go. Let's run the PIO example design. Okay, go into the example design and run the following tests. Oh, okay. Example directory make. Do this. We can do this. Example. Now, where are we going? We're going to user, example, make. And then we want to do this. Okay, and yes. Automatically select the device. Open handled. Okay. We'll do a link test real quick. You ready for a link test? Where's my map? Okay. Okay, let's do a link test. A link test. Sorry, I have not been paying attention. Okay, there's any more chats. Okay. Did not like. Wrote red. Well, that's not good. Let's see what happens here. So we're doing writes. Still just one. Okay. Let's read memory space. Enter address you want to read 0. Okay, what does that look like in here? Yeah, it's still individual transactions. It must be the OS that's just limiting things. Even the tool is not wanting to do harder or larger transactions. What's 9? 2. 2. 1. Okay. Did you do anything interesting when I did that? Yeah, it's still only doing bytes. I don't know what's... Yeah, we're only doing 1 bytes. Okay, let's try again. We do write memory space, do 0 in hex. Yeah, that looks right. And yeah, it doesn't like the link test. At 1357. Yeah. The Raspberry Pi is not treating this the way we expect. Interesting. Okay. So I went through, I built the example design. It doesn't really what's 5 do? It should not be 0. We're just reading. That's interesting. Oh, the Raspberry Pi. We could definitely plug this into a different system and do some different TLB transfers another time. Thank you for coming today. We got to explore more of the application. If you have any questions about PCIe, leave it in the comments. Like, subscribe, share as you see fit. This must be kind of like a how do we explore PCIe? How do we dig down into the subsystem just a little bit more? If there's any other interfaces you want to dig down more into, PCIe is what I know most, but I want to learn more. We're gonna try. There'll probably be other, there's generic LVDS transfers, there's JESD, DisplayPort, it's a little harder to do, HDMI is a little bit harder to do, Ethernet would be interesting, writing something like that from scratch would be hard. But there's any other open source IP we could also look at as well. So thank you for joining me for this hour plus stream. We were able to look at PCIe, and I'm probably going to have to shut it down here. Thank you for watching. Okay, going here. So I'm going to say bye to LinkedIn first. I'm going to say bye to YouTube.